Section 6.1 is concerned with the topic of electromagnetic energy. And this is just a fancy way of saying light energy. So whenever you hear people talking about electromagnetism, they're talking about light. So in classical physics, light is considered to move as a wave. So you probably noticed a few things about waves. If I flick a piece of rope and send a wave through it, the energy moves through the rope, but the rope doesn't change its location. It periodically fluctuates up and down, but the piece of rope stays in place. You've probably also noticed that light can travel not only through an object, but also through empty space. That's why we can see the sun, right? And the stars. The light is able to move where there is no matter. So a guy called James Clerk Maxwell proposed that light is a result of periodic fluctuations in magnetic and electric fields. And this is kind of cool. What Maxwell said is somewhere a particle with a charge, which we would know would be either a proton, an electron, or an ion, moves. And that creates a fluctuating electric field. Now, according to classical physics, whenever you create an electric field at 90 degrees to that, you create a magnetic field. So a fluctuating electric field will create a fluctuating magnetic field. And that magnetic field will push or move our electric field. So our electric field now creates a magnetic field in a different location, which pushes our electric field, and so on and so forth. So what we end up with is a particle moved over here, and our wave or energy propagates through space away from where that particle is moving. So when you're seeing light coming from the sun, that's because charged particles are moving around in the sun, which is pretty awesome. So if we're going to consider light to be a wave, then there are three important parameters of a wave. There's what we call the wavelength, the frequency, and the amplitude. The wavelength is normally indicated using the Greek letter lambda, and the frequency is normally indicated using the Greek letter nu. So the wavelength of light is pretty easy to understand. It's the distance between two adjacent peaks, or alternatively between two adjacent troughs. Peaks are sometimes referred to as crests or ridges of the wave, but I like peak. Now, the kind of light that our eyes can detect typically has a wavelength of hundreds of nanometers, and the Greek prefix nano has the abbreviation lowercase n and means times 10 to the minus 9. And that information is well worth memorizing. The frequency of light, which we indicate with the Greek letter nu, is the number of waves that pass a fixed point per second. So if you want to visualize this in terms of something a little more familiar, think about water waves. Imagine that you were sitting in a boat that was anchored and not moving, and you just counted the number of waves that passed every second. Now, if you had a decent number of waves coming, you might get a wave like, I don't know, every 1 second, 1 wave a second. Well, light has really tiny wavelengths, And typically what we're going to be seeing is around about 10 to the 14 waves per second. So this kind of leads into the next sentence here. Frequency has units of per second, or seconds to the -1. But that's exactly the same as hertz, which has the abbreviation uppercase H, lowercase z. Okay, and like I said, for us, when we're calculating frequencies, we're normally looking for numbers around 10 to the 14. Now, light moves through vacuum with a characteristic speed, and that speed is 3 by 10 to the 8 meters per second. And the speed of light in a vacuum is given a special symbol of lowercase c. Now, when light moves through matter, it will slow down. Not by a lot, but it will slow down by a measurable extent. But in vacuum, light moves at 3 by 10 to the 8 meters per second. I guess if you want to be really fancy and you want to give this out to 5 sig figs, I believe to 5 significant figures, it's 2.9998 by 10 to the 8 meters per second. But I'm more than happy if you just use the speed of light to 3 significant figures. So the speed of light is related to its frequency and wavelength by this little formula here. The speed of light is equal to the wavelength of light times by its frequency. So what we can recognize, hopefully, is that the wavelength and the frequency are inversely related. That is, as the wavelength goes up, the frequency goes down, and vice versa. As the wavelength goes down, the frequency goes up. A common problem is just to interconvert wavelength and frequency. This is a good example of that. It says, what is the frequency of blue light with a wavelength of 450 nanometers? So I always like to begin these problems by writing out the formula. And we're trying to solve for the frequency. So I'm going to reorganize so that we can solve for the frequency. And now I'm just going to put my numbers in. Now, what do we know about 450 nanometers? Well, the lowercase n there means times 10 to the -9. So rather than doing an elaborate conversion, I'm just going to substitute the letter n for its mathematical meaning. So here we go. C is 3 by 10 to the 8 meters per second, and our wavelength lambda is 450 by 10 to the -9 meters. And you can see that meters cancels out, leaving per second. Now I'm going to give my answer here to 2 significant figures. So I'm going to put that into the calculator and round it off to 2 significant figures. And so my calculator answer here is 6.7 by 10 to the 14 seconds to the -1, or I could write 6.7 by 10 to the 14 hertz. Either is valid. And the fact that it's about 10 to the 14 indicates that I'm probably on the right track. This next problem is a little bit more complicated, and what makes it a bit more difficult is that you need to use a lot of metric or SI prefixes. So I would recommend that you go ahead and print out a copy of a table of SI prefixes and make sure you bring that to class with you every day. That's going to be a really helpful tool for solving some of these problems. Okay, so let's get into the problem. It says X-rays have a wavelength small enough to image individual atoms, but are challenging to detect because of their typical frequency. So that's just warming up. It says suppose an X-ray camera uses X-rays with a wavelength of 2.94 nanometers. So I want to recall that nano means times 10 to the minus 9. Okay. Then it says calculate the frequency of the X-rays. Okay, we can do that. But we want to be sure that our answer has the correct number of significant figures. So our wavelength has 3 significant figures. So our final answer will need to be given to 3 significant figures. Now let's have a look here. We can see that the final answer, they're asking for it in petahertz. So petahertz, peta is indicated by an uppercase P and means times 10 to the 15. Okay, so let's look at how we're going to set this up. First thing that we want to do is write out the formula that relates wavelength and frequency. So C equals wavelength times frequency. C equals lambda times nu. We want to calculate the frequency, so we reorganize our equation to solve for the frequency. So the speed of light is 3 by 10 to the 8 meters per second, and our wavelength here is 2.94 nanometers, and you can see I just substituted the power of 10 for the symbol lowercase n. Now that will give me the frequency in seconds to the minus 1, but we're asked to give the frequency in petahertz. So the first thing that I want to remember is that 1 hertz is exactly the same as 1 wave per second. So don't get kind of fooled by that. But now we need to convert to petahertz, which is where our table of SI prefixes is going to come in. So 1 petahertz is the same as 10 to the 15 hertz. And there we go. Our answer to 3 significant figures is 102 petahertz. Okay, so we've talked about wavelength, we've talked about frequency, but what we haven't talked about is amplitude. And what the amplitude of a wave is the height of a crest, or the depth of a trough above or below the center line of the wave. So the amplitude is how high a peak is from the center line of our wave, or how low a trough is from the center line of our wave. The amplitude of the wave, of a light wave, is a measure of the intensity or the brightness of the light. It doesn't affect the color, just how bright it is. The color is affected by the wavelength. So if you're ever given a color, they're kind of giving you the wavelength in code. Often, people will talk about the electromagnetic spectrum, which is a diagram illustrating the typical wavelengths of light that we encounter in our universe. These range from very short gamma rays up to very long, what we call radio waves. And you've probably heard of FM radio and AM radio. There's a section in the middle of the electromagnetic spectrum called visible light, which is what our eyes detect. And our eyes can detect light that ranges from the red, which has a wavelength of around about 740 nanometers, to the violet, which has a wavelength of around about 400 nanometers. So let's just kind of like take a closer look at the electromagnetic spectrum. One of the first things to realize is that as wavelength increases, frequency decreases. So in these diagrams, typically wavelength will increase left to right and frequency will increase right to left. So these arrows here indicate how the quantity is increasing. So typically they'll divide these diagrams up into sort of like 7 to maybe 8 sections. At very short wavelengths and high frequencies, we have gamma rays. And gamma rays are really high energy. Gamma rays can pass through a lot of solid objects. So they can pass through your bones, for example. They'll pass through your entire body like it wasn't there. Gamma rays normally require quite thick lead or concrete in order to stop them. At longer wavelengths than gamma rays, we get X-rays. X-rays are also quite high energy. X-rays will pass through the soft part of your body, but they'll be stopped by the harder parts of your body, like your bones. And so that's why we use X-rays to image bones. What we're really seeing in an X-ray photograph is a shadow where the X-rays are unable to penetrate. At wavelengths a little bit longer than X-rays, we get ultraviolet rays. So ultraviolet rays cannot penetrate very far into matter, but they are quite high energy. That's why ultraviolet light will give you sunburn. It'll cause molecules in your skin to be harmed. And what will happen is ultraviolet rays can actually break chemical bonds. They have enough energy to break chemical bonds. Now, this can be problematic because it can break chemical bonds in your DNA, which can lead to cancer. So that's why we kind of shield ourselves from ultraviolet light in order to prevent skin cancer and sunburn. In the lab, we use ultraviolet light to sterilize our goggles, and basically what we're doing is blasting apart the DNA and proteins in any bacteria or viruses that might be present on the goggles. So ultraviolet light is quite high energy. It can break chemical bonds. At wavelengths a little bit longer than ultraviolet, we get into what we call the visible region of the spectrum. And that starts at violet, and as the wavelength gets longer, it ends in the red region of the electromagnetic spectrum. At wavelengths even longer than visible light, we encounter infrared light, which we sense as heat. So infrared light is obvious that obviously being emitted by an object if we sense heat radiating out of that object. So when we feel the warmth of the sun, we're feeling infrared light being emitted by the sun. At wavelengths longer than the infrared, we head into what most people call the microwave region of the electromagnetic spectrum. So a microwave radiation, you don't experience as heat. It doesn't have quite as much energy as infrared. But what it can do is it can make molecules rotate. So it can make molecules move around. So microwave ovens are used to heat food up for this reason, because microwaves cause random motion of molecules, which is what heat is. At wavelengths longer than microwave radiation, we head into what is often referred to as radio waves, and there's a whole bunch of different categories of radio waves, but collectively they're often called radio waves. These guys are quite low energy. They're buzzing past us all the time, and they really don't interact with us or cause us any difficulties. So, in a typical diagram of the electromagnetic spectrum, we have wavelength increasing from left to right, frequency increasing from right to left, and maybe you noticed that energy is also increasing right to left. So these guys, not much energy, don't really interact with matter very much at all. These guys, lots of energy, and they really blast into matter, and gamma rays in particular can pass clean through matter like it almost wasn't there. Okay, so often you'll have ranking problems where you're asked to relate these names of parts of the electromagnetic spectrum to frequency, wavelength, and energy. So in this type of problem, you just want to be really careful that you don't accidentally get things reversed, because that's a very common issue with ranking problems. So the question reads, a few different types of electromagnetic radiation are listed in the table below. Complete the table by ordering these types of radiation by increasing frequency, wavelength, and energy per photon. So we're going to order by increasing. So that means that number 1 is going to have the lowest value, and number 4 will have the highest value. Okay, so let's begin by just grabbing a copy of the electromagnetic spectrum so we don't get confused. Here it is here, and I'm just going to use this bottom one, and I've made a very careful note of how wavelength, frequency, and energy vary across the electromagnetic spectrum. So when I scan this list, what I realize is that radio waves are the lowest frequency. They are the lowest frequency, which also means that they are the lowest energy. Okay. Now then we've got microwaves, which are right next to radio waves. We've got green light, which is sort of in the middle-ish of the visible spectrum. And then we've got infrared. So infrared and then visible. So if I was to put these guys in order of increasing wavelength, they would go 1 for green, 2 for infrared, 3 for microwave, and then 4 for radio. Now, in terms of increasing frequency and energy, it's going to be the opposite trend, isn't it? Radios are going to have the lowest energy, then microwave, then infrared, and then visible. So I kind of figured it out. I just got to kind of make sure that I don't get confused as I'm entering it now. So I'm going to do frequency and energy first because they follow the same pattern. So whatever number appears in the frequency column, it should also appear in the energy column. And so this is my order, isn't it? Radio, microwave, infrared, and then green light number 4. And I'm just double checking that with my diagram, and that is correct. Now for the wavelength, radio waves are going to be the longest. They're going to be number 4. And the visible green light is going to be the shortest. That's going to be number 1. Let's see if we can get this correct. So radio waves, number 4. Microwaves, number 3, the visible, which is the green light, number 1, and then infrared, number 2, and that's consistent with my diagram. So really, you just got to kind of like take care not to mess up. Okay. So this model of light being waves aligns with a lot of observations. For example, when light travels through one substance into another, its velocity or speed changes. And that gives rise to what we call refraction. That is that the light gets bent when it moves from one medium to another. And that's why glasses work. When the light moves from air into glass, it gets bent, and that allows us to focus the light to a point. What's interesting to observe though, is that the light comes in traveling in a straight line. After it is bent, it continues to travel in a straight line. So we use this in chemistry all the time in the form of a prism. So what happens in a prism is we send in a beam of white light that contains many colors. We pass it through a prism made of glass normally. And because the angle of refraction depends on the wavelength, different wavelengths get bent to different degrees, and we can separate out the different colors. Now, it turns out that the short wavelengths are always bent more than the long wavelengths. So what we end up with when we do this with white light is that the violet light, which has a really short wavelength, gets bent quite a lot, and the red light not so much. And then the others get bent according to their wavelength. So this is a really cool tool that we use all the time. And the reason it works is because light is behaving as a wave. Now, if light was, say, matter instead of being waves, what we find is that when matter moves from one medium to another, where its speed decreases, matter is not refracted. What happens is matter kind of completely changes the way that it's moving. So say we have a stream of particles that are moving in a straight line. When they hit a medium that causes them to slow down, they start traveling on a curved path. This is very different behavior from what waves do. So refraction is an important experiment in confirming or in providing evidence that light is waves. Another interesting thing happens when waves are passed through a slit. When waves are passed through a slit, they might begin with wave fronts that are moving in a straight line parallel to where the slit is, but on the other side of the slit, the wave fronts will be curved. And you might have seen this if you ever see water waves hitting an edge of an object. They'll come in straight, but on the other side of the object, they'll be curved. And matter doesn't do this. Matter is not diffracted in this way. When matter goes through a slit, and we'll have a little diagram of this later on, when matter goes through a slit, it just goes through the slit, you know? It just does that. Okay. Now, this gets really weird when we pass light through two slits, because what we see doesn't immediately make common sense. So if you take a source of light and you put a barrier in front of it that has two holes in it, not just the one, and then at some distance, the other side of the barrier, you can put a screen to see where the light is coming through, you get some really weird phenomena. Firstly, you get bright spots that are way out wide from where the slits are. Isn't that interesting? Way out wider than where the slits are. You'll also have a bunch of black space where no light is getting through at all. And interestingly, directly in front of each slit, it's always black. So that's weird, isn't it? Directly in front of the slit where you think the light would be getting through, it's actually always black. And the little region between the two slits, here it is here, is always bright. So where we know there's a definite barrier, it's always bright. Now, how does that happen? Why does that happen? Well, it's a result of what we call constructive and destructive interference. When two waves meet each other, they might meet such that the peaks line up with the peaks and the troughs line up with the troughs. And if they do, the two waves kind of add together and it brightens the light. And that's what's happening where we see the bright spots. Now, when two waves come together, they might come together what we call out of phase, where a trough meets a peak meets a trough, and so forth. And when they do that, they annihilate. They undergo what we call destructive interference, and they cancel each other out. And that's what we're seeing where we see the black spots. So when we pass light through two slits, we get an interference pattern as a result of constructive and destructive interference. And only waves do this. Matter doesn't do this. If we pass matter through a single slit, you just get a narrow beam of particles. Okay? If you pass matter through two slits, you just get two beams of particles. So under everyday conditions, constructive and destructive interference is not observed for matter. We only see this for waves or for light. So again, that's some pretty powerful evidence that light really is a wave. Another piece of evidence that light is a wave is what we call the Doppler effect. And we can see the Doppler effect when we look at the light emitted by distant stars. So if you look at the light emitted by stars that are quite a way away, what you see is kind of a rainbow, but with a bunch of dark lines where no light is being observed. And these are often referred to as Fraunhofer lines, after Joseph von Fraunhofer, who was studying them in the late 1800s. Now, you probably have heard of the Doppler effect. When waves are emitted by a moving object, they're modified. So if we have a car that is at rest, that's making sound waves, we're hearing the true frequency or the true wavelength of those sound waves. However, when the car starts moving, when it's moving towards us, the wavelength gets kind of squashed up and it sounds more high-pitched. But when the car is moving away from us, the wavelength gets stretched out and it sounds more low-pitched. So waves from objects that are moving away from us they get shifted to longer wavelengths, and waves that are being emitted from objects that are moving towards us, those waves get shifted to shorter wavelengths. And you can kind of do this, experiment yourself if you head out in your car and you get someone to record you while you're wailing on the horn, then you'll observe this effect. So now the Amazon ad is over. So hopefully you were able to hear as the car moved past the observer, the pitch of the car horn was shifted. Okay, so moving sources of waves have a different wavelength depending on whether the object is moving towards you or moving away from you. Now, when you look at the Fraunhofer lines from distant galaxies, what we see is the same spacing of the lines, but all of the lines are shifted to longer wavelengths. That is, they are shifted towards the red end of the visible spectrum. So we say that the lines have undergone a red shift for this reason. So whenever you look for these Fraunhofer lines, you're only ever going to see a red shift and never a blue shift. That is, the objects, the galaxies that are emitting this light have to be moving away from us. And that's how we know that the universe is expanding and not contracting, which is kind of cool. Now, something that's interesting about matter is if you put an element's vapor in a tube and you energize it using either heat or an electric current, it will glow. And that's the way that neon lights work. And neon lights have this characteristic kind of like pinkish glow about them. But the color that you actually get depends upon the element that's in your tube. For example, sodium lamps are a really intense yellow, and you often see them used on like highways and stuff. But those yellow lamps that you see being used as street lamps, they've got a little bit of sodium vapor in them. Mercury lamps give a pretty good approximation to white light. So when you see fluorescent tubes in a classroom or somewhere else and they're glowing white, those tubes often have a little bit of mercury in them. And that's why you might have been told that you can't dispose of fluorescent tubes into regular trash, because mercury is quite toxic. Neon lights tend to have this kind of pinkish, reddish color. So we can put a few ideas here together. If we take the light that is emitted by one of these elements that's in a tube and we pass it through a slit to get a nice beam of light, and then pass it through a prism to use refraction to separate it or disperse it into its individual colors or wavelengths, then what you get is quite interesting. Rather than getting a continuous rainbow, what you get is a series of discrete colored lines that is always the same for a given element, but every element has a different pattern of lines. So I'll show you what I mean. This is called the emission spectrum, and it's always characteristic of the given element. In fact, you can also do it for a compound if you really wanted to. So the emission spectrum of hydrogen has one line down in the red and then a bunch of lines that are in the sort of the green through to the blue, and nothing in between. Sodium, you can see why they use it to get a yellow driving light. It really is just dominated, or its emission spectrum is dominated by these two yellow lines. Helium doesn't look too much different from hydrogen, but there's enough difference in the complexity of the spectra to distinguish it from hydrogen. Neon, as you can see, has a bunch of lines in the red, orange, and yellow, which kind of add together to give it that characteristic pink color. And then mercury has a pretty even distribution of lines across the whole of the visible region. It's kind of lacking a little bit in the deep red, but it's got a pretty good spread. And when you add those colors together, you get an approximation of white. So an emission spectrum shows the colors that are emitted by an element when it is energized. Now, there's an alternative experiment that you can do, is you can take a source of all of the visible wavelengths, so a source of what we call white light. You can pass it through a sample and then pass the light that appears out the other side of your sample through a slit. Again, we can use the wave property of refraction to separate out the light into its different colors and then project that light onto a screen. Now, what we observe in this case is kind of a rainbow, but we get a series of lines that are black where light is being absorbed, where light is being taken in by our sample. And so they call this an absorbance spectra. You guys will get to record this many times. And the black lines indicate where our sample is absorbing light. So this pattern of dark lines is called an absorbance spectrum, and it's characteristic of the sample that the light was passed through. So these are some samples for some of the elements that we were looking at before. So you can see mostly a rainbow with a bunch of black lines where the light is being absorbed. Okay. So everything that we've been talking about so far has depended upon the classical distinction between light or waves and matter. However, around the turn of the 20th century, so this is sort of around the beginning of the 1900s, scientists began to make some observations that didn't fit in with this model. The first problem that scientists had with the wave model of light was that of explaining what is referred to as black body radiation, and this was given the over melodramatic name of being as the UV catastrophe. Okay, so what the heck is a black body? Well, a black body is an idealized object. It probably doesn't exist in reality, right? But it absorbs all light that falls upon it. That's why it's black. So a mirror is not a black body because a mirror reflects most of the light that hits it. So a mirror is not a black body. A window is not a black body because a window allows most of the light that hits it to pass through it. So black bodies are important because any light they do emit has to be a result of something that's happening within the object rather than it just being light that is passing through the object or being reflected from it. Now, what's interesting is the light that's emitted by a black body is observed to depend on one and one thing only, and that's its temperature. So it's intimately related to how the particles in that object are moving around. So these are what we call black body curves, right? And what we notice is that as we raise the temperature of an object, the peak where it emits the most light shifts to shorter and shorter wavelengths, okay? So as the temperature of a black body increases, it is observed to emit in a narrower band of wavelengths, with the peak of that narrower band being at shorter wavelengths. Now, a guy called Wien was able to find an equation that tells you where the peak in the black body curve will be. So the wavelength of maximum emission is equal to B, which is a constant, divided by the temperature of the black body. Now, this is really helpful because it means that you can now just measure where the peak of that curve is, and it directly tells you what the temperature of an object is. So that's how we know how hot things like stars and planets and other objects in our universe are. It's also how those temperature guns that you might get zapped with when you're feeling a little sick work. They're measuring where the peak in your black body curve is, and you can also use them to measure the temperature of other things as well. For example, we know that this is the average temperature of the Earth, and so that as a result, the Earth will be emitting radiation to space in the infrared at around about 10,000 nanometers. So this is the black body curve for the sun. It's often referred to as the solar spectrum. The sun behaves as a black body that has a surface temperature of around about 6,000 Kelvin. And that gives its black body curve a peak in the visible region of the electromagnetic spectrum, which probably explains why our eyes have adapted to work well with visible light. So this is the solar spectrum outside the atmosphere, and you can see it's a pretty smooth curve. It's the orange line there. It's got a few lumps and bumps in it, but it's pretty smooth. They've also plotted here the solar spectrum at sea level. And what you see is that a lot of the wavelengths have been absorbed. In fact, all of them have been absorbed to some degree. But in particular, a lot of infrared radiation is absorbed. A lot of heat is absorbed. All right. Now, what is doing the absorbing? Well, this is gases in the atmosphere. So gases in the atmosphere are absorbing the heat or the infrared light that is produced by the sun, and that's what warms our planet up. If we didn't have an atmosphere, surface temperatures of our planet would be a lot cooler. Now, the problem is that Wien's displacement law has no theoretical foundation. He just found an equation that worked, but he doesn't know why. And no one could explain the shape of the black body curve until 1900. And a guy called Max Planck, and we're going to hear a lot about Planck because we're going to be using a constant that he derived, was able to come up with a formula that explained the shape of the black body curve very well. However, you had to make some assumptions that people weren't altogether comfortable with. So, to explain the shape of the black body curves, Planck said that only certain quantities of light could be emitted by an object. He said that the quantities of light emitted by an object had to follow this formula, which I should say you don't need to know. So the energy that could be emitted had to be a multiple of n, which was a positive integer, h, which is Planck's constant, 6.626 by 10 to the minus 34 joules seconds, and nu, which is the frequency of radiation. So if you think about this, if the energy emitted by a black body can only have specific values, then that means that the things that make up that black body, that is atoms, can only have specific energy values. What we're really saying is that atoms can only have certain fixed quantities of energy. Now, Planck said that the reason why an object emits light, why a black body emits, is a result of the change in energy of an atom. And that's going to be a result of the loss of or gain of one or more quantities of energy. And that quantity of energy has to have a certain specific value. It can't just be any value. It has to agree with the Planck rule. So this is the very first baby step in the development of what we now call quantum mechanics. We still think of light as being a wave, but what we've discovered is that atoms have to have certain specific values for their energy. No one knows why. That's just how it has to be. So, what we say now is that the energy of atoms is quantized. There are only certain specific values allowed for the energy of an atom. So this is kind of like when you are climbing stairs, you are only stable at certain specific heights when you are standing on a stair. Okay, so your height is quantized when you are climbing a flight of stairs. However, if you are moving up a ramp, then your height will be stable at any value you want it to be. That is, your height is a continuum of states. It's not quantized. So this is kind of cool. We found out something really important about atoms by looking at these bizarre black body curves. Now, another important discovery around about this time was Albert Einstein's explanation of a phenomena known as the photoelectric effect. So what happens in the photoelectric effect is we take light, normally UV light, and we shine it on a metal, and we observe what occurs. And what is found is that if the frequency of the light is above a certain minimum, known as the threshold frequency, then the metal surface will eject electrons. However, if you are below the threshold frequency, you never get any electrons being emitted. And it's observed that every metal has its own characteristic threshold frequency. So there are a couple of components of the photoelectric effect that really kind of bothered physicists. The first one was that when you are shining light below the threshold frequency, you never get any current no matter how long you shine the light on the metal. Now, what physicists believed was that you could shine the light onto the metal and electrons would absorb energy, and eventually it would have absorbed enough, it would store up enough energy that it could break free from the metal, right? Now, the other thing that was weird, and it's kind of related to the same idea, is that there was never any time lag between when you shone the light and when you got electrons out. Physicists thought that if you shone less intense light, then you'd have to wait a little while before current would flow while the electrons accumulated enough energy to break through. That doesn't happen. It either works or it doesn't. And what determines if it works is if you're above the threshold frequency. So, Albert Einstein was able to successfully explain the photoelectric effect. But he had to assume that light was not waves, but rather was composed of particle-like bundles of energy called photons. And he kind of put his ideas together with Planck's. He says the energy of a photon corresponds to the change in energy of an atom. That is, the energy of a photon is equal to, or of a photon that is absorbed or emitted, is equal to the change in energy of an atom. So when an atom is emitting a photon, it is losing energy. And when an atom is absorbing a photon, it is gaining energy. The energy of this photon is equal to Planck's constant multiplied by the frequency of the photon. So in the photoelectric effect, where electrons are being emitted, what Einstein is proposing is occurring is that an atom is absorbing a single photon that has enough energy that allows an electron to leave the atom. He said that it's not possible for an electron to store up energy by absorbing multiple photons. So basically, one photon comes in, interacts with an atom, and causes one electron to leave if there's enough energy in that photon. Right? So that's what's happening. A photon comes in, the energy gets absorbed by the atom, the photon ceases to exist. That energy kicks out an electron if it's enough. So here's a sample question where we have to convert wavelength into energy. Now, into energy of a photon, but they don't want energy of one photon, they want energy of a mole of photon. So we should be careful here. So it says, what is the energy of a mole of photons of blue light with a wavelength of 450 nanometers? So I'm going to break this down into a few steps. What we're going to do is we're going to write the equation for energy. And what we see is energy of a photon is equal to Planck's constant times by the frequency of the photon. Now, we don't have the frequency of the photon, we have the wavelength. But that's okay because we can relate wavelength and frequency using this second formula here, can't we? So frequency is equal to wavelength. No, it's not. Frequency is equal to the speed of light divided by the wavelength. So what we're going to do is, instead of writing frequency in our energy formula, we're going to write that. There you go. So that's an important series of relationships. The energy of a photon is equal to Planck's constant times by the frequency, but it's also equal to Planck's constant times the speed of light divided by the wavelength. So let's go ahead and calculate our energy of a photon. So Planck's constant, 6.626 by 10 to the negative 34 joules seconds. The speed of light, 3. Three by 10 to the 8. Meters per second. And then the wavelength, 450 nanometers. So hopefully you can see we're just left with joules. So put that into my calculator. And I get an answer of 4.4 by 10 to the minus 19 joules. And that's pretty typical for a single photon. One photon will have an energy normally around 10 to the minus 18 to 10 to the minus 19 joules. That's not uncommon. Now, we do need to be aware that it asks for a whole mole of photons. So this is for one photon. So for a whole mole, we've got a whole Avogadro's number of photons. So if we want a whole Avogadro's number of photons, it's going to be let me see now. .7 by 10 to the 5 joules. So there we are. Okay. All right. So a little bit more complicated. You've got to have your wits about you, not make a mistake. But if you practice, you'll be fine. So now we can convert energy, frequency, and wavelength for light, not just wavelength and frequency. Okay. Here's a more complicated story problem. It says it takes 348 kilojoules per mole to break a carbon-to-carbon single bond. Calculate the maximum wavelength of light for which a carbon-to-carbon single bond could be broken by absorbing a single photon. Be sure your answer has the correct number of significant figures. So the first thing is we have to recognize that this number is telling us the energy to break a whole mole of photons, right? A whole mole of chemical bonds. So we're going to want to divide by Avogadro's number to get just the energy required to break a single bond. So that's what I've done here. 348 by 10 to the 3 joules is required to break 1 mole of bonds, but we want to know how much is required just to break one bond. So we have to divide by Avogadro's number. And there we have our energy required. So the photons that are being absorbed, or the single photon that is being absorbed to break one bond, has to have energy that is as big as or bigger than this guy. All right, so now we have to turn that into a wavelength. So we know that energy is equal to Planck's constant times by the speed of light divided by the wavelength. So we can reorganize that formula to get the wavelength, and at that point we just have to put our numbers in and plug and chug. Now, once we get our answer, we do want to round to 3 significant figures, and we also need to make sure that our answer is given in nanometers. So Planck's constant times the speed of light divided by the energy gives us the wavelength. And so here's our wavelength, but that's going to be in meters. So now we need to convert it into nanometers, and if you recall, 1 nanometer is the same as 10 to the minus 9 meters. So our light must have a wavelength of 344 nanometers, and this puts it in the UV because the violet begins at 400 nanometers, and UV is really well known for breaking chemical bonds, so this all kind of makes sense. The minimum amount of energy needed to remove an electron via the photoelectric effect is called the work function, and it's normally given the Greek letter phi to indicate it. So this is equal to the product of Planck's constant and the threshold frequency. So phi is equal to Planck's constant times by the threshold frequency. Now, if a photon that is being absorbed by a metal has frequency greater than the threshold frequency, the electron won't be just removed, the electron will be removed with some excess kinetic energy. And this kinetic energy is equal to the product of the frequency and Planck's constant for the incoming photon minus the work function. And yeah, so these are two kind of really commonly used equations in general chemistry too. So let's have a look at a couple of problems applying these formulas. So this question reads, the work function of mercury is 7.22 by 10 to the minus 19 joules. What is the threshold frequency of mercury? So we'll begin by writing out the equation that relates the work function and the threshold frequency. So the work function is equal to Planck's constant multiplied by the threshold frequency, which means the threshold frequency is equal to the work function divided by Planck's constant. So now we're just going to carefully put our numbers in, including our units, and then we'll do the math. Now, frequencies are typically around about 10 to the 14 or so. So let's see what we get here and if it agrees with that. And so I ended up with, to 3 significant figures, 1.09 by 10 to the 15 per second. And that's pretty close to 10 to the 14. So I feel comfortable with that answer. This problem reads, Mercury, and then they give the work function of Mercury, is illuminated with light that has a wavelength of 1.1 by 10 to the minus 10 meters. What is the kinetic energy of the photoelectrons emitted? So I just have to remember my formula. The kinetic energy of my electron is going to be equal to Planck's constant times by the frequency of the light that is shone onto the metal minus the work function. And what we realize is they don't tell us the light, the frequency of the light that's shining on our metal, they tell us the wavelength. But that's okay because we know that C is equal to the wavelength times by the frequency. So the frequency is equal to C on wavelength. So that means that we can write up here C on wavelength where we had frequency, and now that's what we're going to need to do in order to calculate our kinetic energy. So let's go ahead and do that. Our kinetic energy is going to be Planck's constant times by the speed of light divided by our wavelength minus our work function. And let's see what we get. Planck's constant times the speed of light divide the wavelength minus that. And I got 1.81 by 10 to the minus 15, and it's an energy, so it'll be in joules. And I did that twice just to make sure, and it looks like it's correct. Okay, so out of Planck's and Einstein's work, there are two key results. The first, according to Planck, atoms can only have certain specific energy states. According to Einstein, under some scenarios, light behaves as waves. That's what's happening in the phenomena of diffraction and refraction. That's why we see the Doppler effect. However, under other circumstances, such as the photoelectric effect, light behaves as particles. And this is called wave-particle duality. Some phenomena are best explained by considering the light to be a wave. Others are best explained by considering the light to be a particle. So it's a little bit kind of, annoying that we have to have these two different models for light. But that's where we're at, and it's working out okay so far. Okay, so that concludes the video for section 6.1, electromagnetic energy.